So any question from previous discussions? There is no question. So we were talking about frequency response methods for analysis and design of control systems. We know that there are different tools which can be utilized for the analysis and design in frequency domain. These three tools, that is the Bode diagrams, polar plots and Nyquist plots, these are important tools. In our previous lectures, we have learned how to sketch Bode diagrams and how to sketch polar plots. In today's lecture, we shall talk about Nyquist plots. We shall discuss Nyquist stability criterion. We shall learn how to sketch Nyquist plots and how to determine the stability of closed loop systems using Nyquist plots. So basically, stability of closed loop systems using the information about location of open loopholes, that can be determined using Nyquist stability criterion. So that is, if you have a closed loop system with forward transfer function g of s and the transfer function in feedback path is h of s, the closed loop transfer function is given by this relation. So Nyquist stability criterion can be utilized to determine the stability of closed loop system from the information of open loop transfer function. So you remember that the same information could have been extracted using, for example, Routh's criterion and also from the root locus. So what is the additional advantage of this Nyquist stability criterion? So this Nyquist stability criterion can not only tell you about the stability of closed loop system, but it can also tell about degree of stability or degree of instability, that is how much uncertainty can be tolerated without making the system unstable. And furthermore, it can also suggest some technique which can be utilized to improve the stability of a closed loop system. In addition to that, Nyquist stability criterion can also be applied to systems having time delays. This cannot be handled using root locus techniques. So this is one additional advantage of this Nyquist stability criterion. So before we talk about the Nyquist stability criterion and we learn how to sketch the Nyquist plots, we revise our basic concepts of mapping. You have already studied these mappings in your previous courses, so we just revise these concepts. What is mapping? For example, if you have a complex function, and you take a point in S plane and substitute that point in this function, you will get another complex number, and this is called mapping. For example, you have this point in S plane, S equal to 2 plus j1. If you substitute this complex number in this function, that is substitute S equal to this, you will get another complex number. That complex number is given over here. How do we obtain it? Substitute S equal to 2 plus j1 into this expression. So here instead of S you have 2 plus j1 and this plus 1 here, likewise in the denominator, and multiply it by its complex conjugate, and then you get 4 minus j2 divided by 2, which is 2 minus j1. So this is called mapping. Graphically, you have S plane. S plane is a complex plane with real axis and imaginary axis, and you have another plane, f of S plane, which is also a complex plane with a real axis and imaginary axis. In this plane, you had a point over here, which is 2 plus j1, and you obtained its mapping in this plane, and that was mapped over here. 2 minus j1 is over here, and this is called mapping, and this function is called mapping function. So is it clear? This concept of mapping is clear to all of you. Over here we have mapped a single point. If you have many points, you can map all those points using the same technique. Substitute that point in the mapping function, you will get another complex number. You can represent that complex number in this complex plane. So you can not only map points, you can also map contours. What is a contour? Contour is a set of points. So here you have this contour, we name it contour A. This contour is composed of many points, and what you can do is that you can obtain the mapping of each of these points on this contour in this f of s plane, and you will get another contour in this complex plane. This is called mapping of contours, and this mapping has certain properties. First property is that if you have a closed curve here in S plane and you map it in this plane, you will also get a closed curve in this plane. Is it clear? You had a closed contour in S plane, you utilized some mapping function and mapped this contour in this plane, you will again get a closed curve over here. That is, for a given continuous closed path in S plane, there corresponds a closed curve in f of s plane. The condition is that this curve does not pass through the poles of this function, that is, does not pass through the singular points, which are basically the poles of that function. Furthermore, if you have this contour and this mapping function, for example, has some 0 at s equal to z1, that is indicated over here. So this closed curve, if it does not enclose this 0, if this curve does not enclose this 0 of the mapping function, and you will get a corresponding closed curve, and the direction means if we map, for example, first we map this point and then this point and then this point, that is, we are moving in clockwise direction. So corresponding mapping in this plane will also be clockwise. Is it clear? Here you have a clockwise contour, corresponding to it you will also have a closed curve which is clockwise direction, provided that this mapping function has only zeros or only poles, and this contour does not enclose this pole and 0. The same is the case for pole. You have this mapping function with some pole over here, pole at P1. You had a closed contour, and you moved in clockwise direction. Corresponding to this, you get another curve, a closed curve, and this closed curve is also in clockwise direction. So this statement is written over here: clockwise direction for mapping of the points on contour A. Contour B maps in clockwise direction if f of s has just zeros or has just poles that are not encircled by the contour. Is this statement clear?
Yes, sir.
What if this closed curve encircles a pole of the mapping function? What will be the situation? If this closed curve encircles a pole of the mapping function, then mapping of this contour will be this mapping will be again a closed curve, but this closed curve will encircle origin of this plane. Direction is counterclockwise and it encircles the origin as well. Previously, the closed curve was not encircling the origin. Here it encircles the origin and this direction is counterclockwise. Similarly, if you have closed curve in S-plane which in circles is 0 of this mapping function, what will be situation? You will again get a closed curve, but now this closed curve encircles origin in clockwise direction. So what if the mapping function has both poles and zeros? What will be situation in that case? This mapping function has both pole and zero enclosed by this contour, and corresponding to it there will be no encirclement of origin. That is, one encirclement was due to pole and another in the opposite direction by 0. So net encirclements, no net encirclement, that is encirclement of origin is 0. And in general, if this mapping function has multiple poles and multiple zeros, then the encirclements of origin, number of encirclements of origin, will be equal to the difference in the number of zeros and poles. That is, number of encirclements will be equal to z minus p, where z is the number of zeros of this mapping function enclosed by this contour, and p is the number of poles of this mapping function enclosed by this contour. So the number of encirclements of origin will be equal to z minus p. So n is number of clockwise encirclements of this mapping contour of this point, and what is z? Z is the number of zeros of this mapping function enclosed by this contour, and what is p? Right. So p is the number of the poles of this mapping function enclosed by this contour. So how we can utilize these mapping theorems, concepts of mapping, for the stability analysis of closed loop systems? For example, here you have a closed loop system, and closed loop transfer function is given over here, and we take this f of s to be a mapping function. That is, this 1 plus g of s into h of s, we take this to be the mapping function, and the contour that we take in the S plane is this D shaped closed curve. This D shaped closed curve with radius equal to infinity. This radius equal to infinity. This closed curve, this closed path, this is also called Nyquist path. We take this path in the S plane and use this mapping function and obtain its mapping in f of s plane, obtain its mapping over here. You see that this path, its radius is infinity, so it encompasses the whole right half s plane. This radius is infinity, so it encompasses the whole right half s plane. So this encloses all the zeros and poles of f of s which are in the right half s plane. So since this encompasses the whole right half s plane, so how many poles and zeros are enclosed by this? All the poles and zeros of f of s which are in the right half s plane, those are enclosed by this path. So this criteria is still applicable that we have studied, this mapping theorems. What is n? N is the number of clockwise encirclements of this origin in this plane. So that is clockwise encirclements of this point. What is that? Zeros of zeros enclosed by zeros of this mapping function enclosed by this path. That is zeros of this function which are in the right half s plane. What is p? Right, number of poles of this mapping function which are in the right half s plane. because all the poles which are in the right half S plane will be enclosed by this path. So this is the number of poles of f of s in the right half S plane. Another very important observation is that zeros of this function are the, what are zeros of this mapping function? Right. So zeros of this mapping function are the closed loop poles, poles of this closed loop transfer function. Zeros of this function are the poles of this closed loop transfer function. That is, in this expression, this z is also equal to number of closed loop poles in the right half S plane. And what are the poles of this mapping function? What are poles of this mapping function? Poles of this mapping function are also the poles of open loop transfer function. Poles of this mapping function are the poles of open loop transfer function in right half S plane. How? For example, consider this loop gain, open loop transfer function. This g of s is the ratio of a numerator polynomial and a denominator polynomial. Let's write it as a ratio of n1 and d1. Likewise, h of s is also a ratio of numerator polynomial and a denominator polynomial. So this is g of s into h of s. What is 1 plus g of s into h of s is given by this relation, which is written over here. So what are the poles of open loop transfer function? Poles of open loop transfer function are the roots of polynomial in denominator, which is d1 into d2. And what are poles of this thing? So poles of this thing are the same as open loop poles. So here poles of f of s in the right half S plane, those are the same as open loop poles. So is this clear? So what we shall do is that to determine the closed loop stability of a system, we shall map this contour in f of S plane using this mapping function. We shall count the number of encirclements of this point, and once number of encirclements is known, and this generally number of open loop poles of its system in the right half plane, that is generally known. So if these two things are known, we can determine the number of closed loop poles in the right half S plane. That is, we can determine the stability of the closed loop system. Any question up to this point? So what do we mean by encirclements? So let's see this graph. So to determine encirclements, what we do is that we draw a vector with one end at origin, and other end on the graph. We move this end on the graph. So how much degrees this vector will rotate? If we, for example, start from here, move along this graph, and again reach to this point, so 360. So in which direction? Clockwise direction. So we say that this point is encircled by 360 degrees in clockwise direction, or there is one encirclement in clockwise direction. Is it clear? So we shall see it for other examples as well. So now this concept is clear. We apply it to some examples, but before we apply it to some example, let's simplify it a little bit more. In this case, what was mapping function? We have used this mapping function. And if instead of using this mapping function, if we use this as mapping function, what will be difference between the graphs that we obtain? So there is some answer. यहाँ पे कुछ किसी ने बोला है, तो that is correct. थोड़ा ऊंचे बोलें. So there will be a shift of 1 towards left. So the shape of the graph, if we use this mapping function or this mapping function, the shape of the graph is the same. The only difference is that it will be shifted to the left by 1 unit. So what we can do is that instead of using this as mapping function, we can use this mapping function, and instead of counting the number of encirclements of origin, we can count the number of encirclements of which point? -1. You are right. So this was using the mapping function 1 plus gh, and this is the graph in gh plane. So both the graphs have the same shape. The only difference is that this graph is shifted towards left by 1 unit. So we can again apply the same, we can use this same relation. However, now instead of counting the encirclements of origin, we can count the encirclement of this point. This point is called the critical point, and again use the same relation. Obtain the mapping of this function, count the number of encirclements. So if we know the number of encirclements, we know the number of open loop poles in the right half S plane, we can determine the number of poles, closed loop poles in the right half S plane, and therefore we can determine the stability of the closed loop system. We apply this concept to some examples. Here is a system, closed loop system, with g of s into h of s given by this relation. What we shall do is that we shall take this Nyquist path, which encompasses the whole right half S plane, obtain its mapping in g h plane. We shall count the number of encirclements. We already know how many poles this mapping function has in the right half S plane, and therefore if the number of encirclements is known, number of poles of open loop transfer function in the right half S plane is known, we can determine the number of poles of the closed loop transfer function in the right half S plane, and therefore we can determine the stability. So now the open loop poles are here. One pole is at s equal to -2, and another pole is at s equal to -4. So how many poles enclosed by this Nyquist plot? So no open loop pole is in the right half S plane, therefore this P is equal to 0. So now the question is how to map this path over here. One strategy is take each point one by one and substitute it in this mapping function, obtain corresponding point over here, and then so that is impossible because you have infinitely many points. So what we shall do is that we have already learnt polar plots. And what was polar plot? In the polar plot, what we had done is we had substituted frequencies ranging from 0 to infinity and obtained their corresponding mapping in this plane. So mapping of this part of the Nyquist path is the same as the polar plots that we have already learnt. What about mapping of this thing, this negative imaginary axis? Mapping of this negative imaginary axis will be just mirror image of the mapping of this positive imaginary axis. So and we shall also learn how to map this D-shaped curve. So mapping of the positive imaginary axis is the same as polar plots that we have already learned. Mapping of the negative imaginary axis is the mirror image of the mapping of the positive imaginary axis. So let's obtain the mapping of this positive imaginary axis. So how would you map it? What was strategy? Right. So we substituted s equal to j omega and then obtained a few points. The easiest points were corresponding to omega equal to 0. If we substitute omega equal to 0, we have this 1 divided by 8, and written in polar form, this is 0.125 angle 0 degrees. We have already learned how to sketch polar plot for this transfer function. This example was also taken over there. And this point, where is that mapped? That is somewhere here on the positive real axis, and another convenient point corresponds to omega equal to infinity. Corresponding to omega equal to infinity, this is again by mistake, so you have a 0 angle minus 180 degrees. This exponent 2 is by mistake. Where is this point mapped? Over here, and we can determine a few more points. Convenient points are imaginary axis crossover and the real axis crossover. To determine those crossover points, we shall rationalize this thing. So this thing multiplied by its complex conjugate, and after multiplication we have this relation. We substitute the real part to be equal to 0 to get the crossing of the graph on the imaginary axis, and this gives us omega equal to square root of 8. And likewise, to determine the crossing of the graph on the real axis, we substitute the imaginary part equal to 0, which gives us omega equal to 0 and omega equal to infinity. Corresponding to these points omega equal to infinity and omega equal to 0, we have already determined corresponding mappings. We determine the mapping of this point, and g of j omega into h of j omega at this frequency, that is equal to minus j 0.056. So the mapping of this positive imaginary axis is over here. We have 3 points, 1 point over here, 1 point over here, and 1 point over here. Joining these 3 points and additionally using some intuition, we have this graph, which is very rough sketch of the mapping of this positive imaginary axis. Next comes the we have started from this point, moved in this point, and now comes the mapping of this semicircle. How to map this semicircle? This entire semicircle can be represented by this equation, that is s equal to r e raised to the power j theta, where r tends to infinity, radius of this circle is infinity, and angle varies from pi by 2 to minus pi by 2. Corresponding to this point, we had angle of pi by 2, and then this point corresponds to angle 0, and then this point corresponds to angle minus pi by 2. So this entire semicircle is represented by this equation, where r tends to infinity and theta varies from pi by 2 to minus pi by 2. We substitute this s into this transfer function. So g of s into h of s at s equal to r e raised to the power j theta, that is given by this relation. And since r tends to infinity, we can just ignore this small number. We can also ignore this small number. So that is the same as 1 over r e raised to the power j theta multiplied by r e raised to the power j theta. And that is we have this situation, 1 over r square e raised to the power j theta, which can be written in this polar form. Angle of this thing is 2 theta, which brought in the numerator becomes minus 2 theta. So magnitude 1 over r square and angle minus 2 theta. So where is this semicircle mapped in this plane? Right. So for all these points, r is equal to infinity. So magnitude of this complex number will be equal to 0. What will be angle? Angle will be minus 2 multiplied by angle of this number. For example, angle corresponding to this point here, what was theta? Pi by 2. So mapping of this point will be minus pi, 0 angle minus pi. So anyway, all the points on this semicircle will be mapped over here, will be mapped to a single point in this GH plane. We have mapped this segment of the contour, we have also mapped this segment of the contour, and we are left with mapping of this segment, and that is just the mirror image of this mapping, and that is represented over here. So this is a beautiful shape, of course. Dil, heart, bilkul. So now we have the complete mapping of the Nyquist path in GH plane. We can apply, you can also use MATLAB commands to obtain the Nyquist plots. You simply enter the transfer function and the command Nyquist will plot the Nyquist plot. Here is the Nyquist plot obtained using MATLAB. And this is the sketch of the Nyquist plot that we obtained using only a few points. We can apply this relation to determine the stability of the closed loop system. How many what is P? P is equal to 0. We need to count the number of encirclements, and to count the number of encirclements of this critical point, what we do is we make a vector. With one end at -1 and other end on this graph. We move this vector on this graph and see how much degrees this vector has rotated. For example, if corresponding to this point, this vector has rotated by some degrees. Here it has rotated further. This vector has rotated by some degrees, and then it rotates back. So how much is the net rotation as we move this vector along this curve? Net rotation is 0. Net rotation, because initially it moved downward, then it moved upward, and then it moved further up, and finally it moved again downwards. So net rotation in this vector is 0. So number of encirclements is equal to 0. So then what is Z? This P is equal to 0, N is equal to 0. What is Z? Z is equal to 0. What is Z? Right. So this Z is number of zeros of f of s enclosed by the contour, which we learned earlier is also equal to the number of closed loop poles. So in this case, closed loop poles enclosed by this contour is equal to 0. What about stability of closed loop system? So closed loop system is stable. No pole of the closed loop system in the right half plane, therefore closed loop system is stable. Is it clear? We take a few more examples. Here we have another transfer function, and we want to determine the stability of the closed loop system. The procedure you already know. You will map this this Nyquist path in this GH plane. We will count the number of encirclements. So for that purpose, the open loop poles of this transfer function are over here. One pole is here and two poles are here, and then mapping of this segment of the contour is the same as the polar plot. So for that purpose, we obtain g of j omega into h of j omega. H of j omega is missing over here. That is here. You take a few points. For example, omega equal to 0 results into this point, and omega tends to infinity. We get this point. You also determine you have 1 point over here, 1 point over here, and you also determine a few more points by rationalizing it and substituting the real part equal to 0. You get these frequencies. Substituting the imaginary part equal to 0, you get these frequencies. We have already done this polar plot for this particular transfer function, and corresponding to this frequency we have this mapping, and corresponding to omega equal to 1 we have this mapping. So you have a few more points, this point and this point. Those are depicted over here, and now joining the information of these points, you have this mapping of the positive imaginary axis. For this semicircle, you again replace it by s equal to r e raised to the power j theta, where r tends to infinity and theta varies from pi by 2 to minus pi by 2. You substitute this in this transfer function, you get this thing. Again, since r tends to infinity, you can just omit this thing, you can omit this quantity, you can furthermore omit this quantity, because here you have square of r and here you have simply r. So this is the mapping of this semicircle in the GH plane, which is written in polar form is 0 angle minus 3 theta. So again, this semicircle, entire semicircle is mapped to a single point. What is mapping of the negative imaginary axis? The mirror image of this one, so that is over here. And now you count the number of encirclements of this point minus 1. Where is minus 1? This point is minus 0.05 and minus 1 will be somewhere to the left of it. So how many encirclements? How many encirclements of the critical point? There is no encirclement. So P is the number of the open loop poles enclosed by this path, that is also 0. N is equal to 0. So Z is equal to 0, which means that the closed loop system will be stable. So any question up to this point? There is no question. So we shall continue this discussion in the next lecture, inshallah.